Hello, so today we are going to understand the growth kinetics. So first of all, what is growth kinetics? It is a study and analysis of quantitative aspect of growth in living organism. For instance, microorganisms, cells or population. So in this involves the examination rate at which this organism grow, reproduce, increase in size and number over time. Okay, so that means the which time they grow and how much time it will take for reproduce. For example, bacteria it will take 20 minutes, yeast it will take 90 minutes. Okay, so and we if we're talking about humans, so it cells taking 24 hours. Okay, the next growth kinetics involves the measurement analysis of various parameters which is associated with the growth. So first is growth rate, doubling time, biomass, cell density and population size. Okay, so all of these parameters are often studied in relation to factors such as nutrient availability, temperature, pH, oxygen level, the environment condition that influence the growth. So for example, if we calculated the bacteria population, so with an initial population size of cell it is 100 and find population size of 500 after a period of time, for example 5 hours. So we can calculate this bacteria growth rate by the applying this equation delta n is equal to n2 minus n1. So first n2, that means the final population size of cells. So here it is 500 cells. Okay, then minus initially population size of it is 100. So after the 5 hours it will get the 400 cells. So the R is equal to delta n slash n1 and divided by t. So delta n is 400 and n1 it is initial population size 100 and divided 5, that means time, which time that cells are producing number of size. Okay, so 4 into 5 is equal to 0.8 cells per hours. Okay, so therefore 0.8 that means 0.8 is the growth rate of bacteria population. Okay, in this particular example. Okay, so we're talking about the kinetics of growth and substrate utilization in batch culture. So first of all, we know that what is the batch culture. So batch culture nothing but it is a closed culture system that contains initially and limited amount of nutrient. That means if for example if you prepare the batch culture, so initially nutrient it is 100 ml, so that is the close, then you can't add any other nutrient entire the process. So the inoculated culture will pass through the number of phases. So it is the basic concept, like first phase is lag phase, then log or exponential phase, deceleration phase and stationary phase. Okay, so growth that pass on the mainly 4 phases. Okay, so here it is the inoculated culture that might be bacteria, fungi. So this is the diagram of batch or stirred tank fermenter. Okay, so particularly we're talking about the batch culture fermentation process. So as you see here that before start, okay, so nutrients and inoculum are added into the culture vessels, right? Then during the process nothing is added or removed during the process. Okay, after end broth is collected for the downstream process. Downstream process, that means that cell separation or we get the desired product. Okay, so we further proceed this in downstream process. Okay. So in batch culture there are 4 phases. So first phase is lag phase, or it also called a time of adaptation. Okay, after inoculation there is period during which it appears that no growth take place. Okay, so initially when you inoculate your sample or inoculum, for example yeast, bacteria, fungi, okay, so initially period you can't see the growth. Okay, but after the some periods, for example 1 hour, okay, 1 hour, that you show the slight turbidity. Okay, so this period is referred to okay, so when you inoculated your culture and no growth take place, that means this period it is the lag phase. Okay, and may be considered as a time of adaptation. Okay, so in the commercial process, that means industrial process, most of the industry reduce the lag phase. Okay, that means length of the lag phase should be reduced as much as possible. Okay, this may be achieved by using suitable inoculum, okay, and culture condition. Okay, so what is the suitable inoculum? Okay, so that means if when you inoculated your culture, so that means that 1 ml, okay, that your culture containing at least in one colony that contains the 10⁶ to 10⁸ cells. Okay, and your culture inoculum size should be 10⁶ cells per ml. So that is the suitable inoculum, which is reduce the lag phase. Okay, here you can see here Bacillus subtilis. Okay, the picture of bacteria that growing on agar plates. Agar plate. Okay, culture condition. Okay, the culture condition should be temperature, pH, O2 and nutrient. It's required for the growth of the bacteria. Okay, so there is the lag phase of inoculate culture. Okay, you can't see here the turbidity, that is only nutrient growth, and just you inoculated your sample. So now second phase is exponential phase. Okay, so what is log or we can say the exponential phase? So after lag phase, the following period during which is the growth rate of the cell gradually increase. Okay, so this is a gradual increase, not a drastic increase. The cell growth at constant, okay, particularly that is cell growth is constant. Okay, that means 20 minutes. The cell divided at 20 minutes and they produce 2. Further 20 minutes they produce 2. Okay, so growth rate is constant, maximum rate. Okay, and this period is known as log or exponential, or you can say the logarithmic phase. Okay, so in this phase, increase in microbial biomass concentration will be proportional to the initial biomass concentration. That means initial bioconcentration, that means your provided inoculum culture. If you added we can say standard procedure that in 100 ml you add 1 ml of 1 ml which is contain the 10⁶ cells. That is the standard procedure and standard volume for the maximum growth. Okay, so if you prepare the 1 liter of fermentation any products, so 1 liter, that means you must be added 10 ml, okay, into the 1 liter broth. Okay, so that you will get the huge biomass concentration. Okay, so here is the formula: dx upon dt proportional to x. Okay, so x is the concentration of microbial biomass, that is calculated by gram per decimeter. Okay, t is the time, it particularly calculate the hour. Okay, you can also calculate by the minutes. Okay, d is the small change. Okay, so here you see here that culture turbidity. Okay, so that means that microbes are go into the log phase and they produce their colony, and culture shows it. So this is the equation. This, okay, so a value 2.7182 put into this equation. Okay, so finally we multiply the initial population size by the exponential function. For n3 is equal to 100 into 1.63. Okay, n3 163. Thereafter, after 3 hours in the exponential phase, estimated population size would be approximately 163 cells. Okay. So now next is some of the organism and their mu-max value. Okay. So this is the Vibrio nitrogens, highest mu-max 4.24. So now next is the third phase, desiccation and stationary phase. Whether the organism is unicellular or mycelium, the foregoing equations predict that the growth will continue indefinitely. Okay, So the stationary phase in batch culture is at the point where the growth rate has declined to 0. Okay, in stationary phase in batch culture, okay, the growth rate is 0. Okay, consumption of nutrients and the excretion of microbial products in which influence the growth of organism. Okay. So certain growth rate of culture decrease until growth ceases. Okay, cessation, that means death. The growth may be due to the depletion of some essential nutrient in the medium. Okay, so we can say the substrate limitation, accumulation of some autotoxic product of the organism in the medium, toxic limitation, and combination of the two. That might be happen like substrate limitation as same time is toxic limitation. Okay, so here it is the nature of the limitation of growth may be explored by growing the organism presence of range of substrate concentration. Okay, so plotting the biomass concentration in stationary phase against initial substrate concentration. Okay, so here in figure 2.3 you can see that the biomass concentration of stationary phase it is Y, and X it is the initial substrate concentration. So here is the A to B. So initially substrate concentration is increased and the biomass is also increased, okay, at stationary phase. Now the substrate limiting, okay, in stationary phase substrate limiting, the situation may be described by the equation X is equal to Y SR minus S, where X is the concentration of biomass produced, Y is the yield factor, gram biomass produced, gram substrate consumed.